All right, so welcome back to physics lecture number 2. So just a reminder that the assignment on this lecture will be due by the end of lecture day. Okay, so quickly, last time we talked about temperature. What's the definition of temperature in physics? It's the high value of something with hot object and low value of it with cold object. That's called temperature. We use T for the symbol of temperature, and SI unit for the temperature will be Kelvin, okay, not Fahrenheit or Celsius. And you can use thermometers to measure temperature, and you can have different scales. You can have like Fahrenheit scale, you can have Celsius scale, or you can have Kelvin scale. And we talk about how to make conversions from one scale to another scale. So 9 degrees in Fahrenheit will be about 5 degrees in Celsius. That's the scale. And Celsius scale and Fahrenheit, the same 5 degrees in Celsius will be corresponding to 5 degrees in Kelvin. And if you are converting from one temperature scale to another one, you can come here and then pick one of the equations, the correct one, to do the conversion of the temperature. We also talked about the thermal expansion, which simply, if you have a material, when temperature increases, it's going to be expand in certain directions in one dimension as well as in two-dimensional and three-dimensional as well. So if you just look at certain direction, one direction, then we are looking at the one-dimensional expansion delta L and equal to constant times delta T. Okay, the change in length is proportional to the change in temperature. The alpha here, called coefficient of linear expansion, is defined as the change in the length over the original length divided by the change in temperature. So that's how you get the alpha. So alpha will be having the dimension of temperature inverse. You can use either Kelvin inverse or Celsius inverse. You can also have, this is just the SI unit, but you can also have Fahrenheit inverse, okay, as the unit of it. And the material will also expand in two-dimensional. So if you are looking at the two-dimensional expansion, then we are looking at the change in the areas, A. So delta A, we showed last time, this is proportional, approximately equal to twice of the linear expansion coefficient times the original area and times the change in temperature. And the same apply to the three-dimensional thermal expansion. You can also do the same algebra. You can assume it's a cubic, and then you're going to have the three edges expand in all directions with respect to the temperature change delta T. You're going to, again, ignore the higher order terms. Then at the end, the volume expansion is going to be approximately 3 times of the linear coefficient times the original volume times the delta T, the change in temperature. This beta is called volume expansion coefficient. It's equal to 3 times of alpha. So move on today, we are going to talk about heat transfer, specific heat, and calorimeter, okay? So we know that if you have two objects with different temperatures, if you put them in contact, for example, you have soda and you have ice, so you pour the soda into the a glass and then you put the ice in, and the soda initially is having higher temperature than the ice, right? So then when you put the ice in the soda, you actually bring the temperature of the soda down, okay? So there's actually exchange of heat here. So heat in physics and also in chemistry, it's the same thing. It's defined as the transfer of energy due to temperature differences. So soda and ice, they have different temperatures. There's a different temperature difference. So then heat will transfer from one soda, in this case, to the ice, okay? Naturally, the transfer of the heat, the energy, is going to be going from the higher temperature object to the lower temperature object, okay? So in this class, we'll use symbol Q, capital Q for heat. And because heat is transfer of energy, so it's equivalent to energy change. So then it should have the same units, SI unit as the energy. So energy would have the SI units of joule that we learned last semester. So J for that. So there's also other units can be used for heat. So one of them is calorie. So 1 calorie is about 4.186 joules of heat, or sometimes you can just say 4.2. But the more digits you keep, the more precise result you are going to get. Now, the calorie is actually exactly defined as the 1 grain of water. If you increase its temperature by 1 degree Celsius, then the heat needed to add it to it is 1 calorie, or 4.186. Now, in this case, it has specifically to be increased temperature from 14.5 degrees Celsius to 15.5 Celsius for the definition. And if you have wondered why the energy or heat has the units of joule, then it's actually due to the work done by James Joule a couple hundred years ago. So he demonstrated that actually the heat is equivalent of energy. So in his experiment, he has these two weights here, and he has the ropes wrapped around this spinner over here. So you can imagine as the weights are released, they are going down. So their potential energy, gravitational potential energy is going to be decreased, right? Now, the amount of decrease you can calculate depending on how much height descent happens for the weight, right? The weights, so h. So you can calculate mgh. In this case, you have two weights, so 2 times mgh, okay? And the descent of the weights will actually drive this spinner. So then you actually will stir the water here. Then you can measure the temperature of the water. And then you can calculate how much energy actually is added to the water, because after this is the water has been stirred, the temperature of it will increase. Okay, so then the heat added can be actually calculated. So he demonstrate that the gravitational potential energy change of the weights actually is equal to the heat added to the water here. So then he proved that heat and energy transfer is equivalent to each other. Okay, so due to his work, so then scientists honor him by using his name as the unit of the heat or energy, joule. Okay. All right. So if you have heat added to an object, then the temperature of the object will increase. If you have heat removed from the object, then the temperature of the object will decrease. So put this into equation, we can say Q, heat added, is equal to the mass of the object times C, which is called the specific heat capacity of the material, and times delta T, the temperature change. Okay. Sometimes you see people just use Q equal to capital C times delta T. So in that case, then capital C is the heat capacity. The specific heat capacity, that means heat capacity per unit mass. Okay. So in that case, capital C equal to M times C. Anyway, so going back to this equation, so he added equal to the mass of the material or object times the specific heat capacity times delta T. Okay. So the SI unit for C, specific heat capacity, you can see from here. So Q has a SI unit of joule, M has the SI unit of kilogram, delta T has a SI unit of degree Celsius or Kelvin, because this is delta T, so change in temperature. When we are talking about change in temperature, if you calculate in Celsius, it's going to be the same that you calculate in Kelvin, okay? Because Celsius temperature is just a shift of 273.15 degrees from Kelvin, okay? All right, so SI unit will be either joules per kilogram times Kelvin or joules per kilogram times degrees Celsius. All right, here's the a table of the specific heat capacity for different substances over here. So typically, you have solids like metals, they have smaller heat capacity than if you have other materials and in liquid. So for example, here. All right. So one thing to point out is water. Water has a specific heat capacity of 4186 joules per kilogram per degree Celsius. Compared to the metals, they are much smaller than water. Okay, so water actually has a very large heat capacity. That means if you want to increase the temperature of water, you need to add a lot more heat. So the other way around is also true. If you want to decrease temperature of water, then you need to take off a lot of heat from water. Okay, so because of that, water actually is used as a very good coolant. Okay, so that means it actually can maintain the temperature of the surrounding area. So it will not go um, jump like high, very high up or jump very low down in that sense. Okay. On the other hand, metals are easy to heat up or cool down in that sense. If you are working on a problem, you can come to this table and then check the specific heat capacity of certain materials if it's not given. Okay. All right. So the application of heat capacity, because a lot of times people will be interested in finding what will be the specific heat capacity of an unknown object. Okay, you can actually specific heat capacity is actually one of the intrinsic property of a material. So if you know this is a pure material, then you can look it up and then to see to find what will be the specific heat of it. Okay, now if you are given an unknown material, you can use a so-called calorimeter to measure the specific heat capacity of it, and then find the value of it, and then look it up on the table and identify this material. Okay, so basically, a calorimeter is actually it's going to be a light-weighted device. It's well insulated. Usually, it comes in the form of flask or beaker or whatever, well insulated. That contains water because water has a well-known heat capacity. Okay, then you put the unknown object into it. You wait for a little while, and then the object and the water will come to thermal equilibrium, and then you'll measure the temperature of the equilibrium status. Of course, you first have to measure the temperature of the water initially, as well as the object initially. Okay, so then use those informations, you can find the specific heat capacity of the object. And we are going to do this in the lab, in the second lab. Okay, so you're to be doing that. If not, then we'll be in the third lab. So basically, the water and the object should have different temperature initially. So one is having higher temperature, we call it hot object, and then the other one will be then having lower temperature, we call it cold object. So the heat change Q in this case for the cold object plus the heat change for the hot object Q hot, it should be equal to 0. So keep that in mind. So one object will actually, its heat actually will be plus, and then the other one will be minus. So in this case, Q cold will be plus, okay? And then Q hot will be minus because hot object gives heat to the cold object. So hot object loses heat. On the other hand, cold object actually gains heat. So it receives heat from the hot object. So then they will come to 0, okay? So there's no heat loss in the process or no excess heat here. So the two should add up to be 0, okay? Let's take a look on one example, and then you'll see then how actually to apply this. The heat changes for the two objects in contact should be equal to 0 to find specific heat capacity of the unknown object or the unknown heat capacity of the object. So for example, this one says you have 225 grams of lead ball at a temperature of 81.2 degrees Celsius is placed in a light calorimeter containing 155 grams of water at 20.30 20.3 degrees Celsius, it says find the actually equilibrium temperature in this time, and it gives you actually the two specific heat capacity, right? So you can imagine now, instead of giving you the lead, if you are given an unknown material, then this specific heat capacity will not be given. So you can actually start with the initial temperatures of the two and then measure the final temperature, right? So in that case, then you can work around to find the specific heat capacity. But in this problem, you're actually given the two specific heat capacities and the initial temperatures, and then you'll be looking for what will be the final temperature, okay? So this is just a tweak of the problem, but let's take a look on this one. So let me write down the notes here, okay? So the mass of the, bring this logic over here. The mass of the lead, if we use chemical symbols, lead for Pb is 225 grams, okay? The mass of the water, I'm going to use chemical symbols as well. H2O is actually 155 grams. Initial temperature, right? So temperature of the lead initially is 81.2 degrees Celsius. Temperature of water, H2O, is initially 20.3 degrees Celsius. Specific heat capacity for the two, so C for Pb is initially, or it's actually 128 joules, kilograms times Kelvin. Now specific heat for the water is going to be 4186, okay? So you'll probably see this number quite often. Specific heat capacity for water 4186. So if you could remember, that's great, okay? And that'll be much better than looking it around every time. All right, so you have the two in contact, right? So they will reach equilibrium in a while. So let's say Q, the heat added to the lead or subtract to the lead. If it's added, then this one will be positive. If it's removed, then this will be negative, right? Plus Q of water actually is going to be equal to 0. Now the heat equation for heat, if you remember, is going to mass times C times delta T. Okay, delta T will be then the final, in this case, the equilibrium temperature. So you can call it just T, or you can say T final, or maybe TE, however you want. Okay, so it should be this guy minus the initial temperature. So for example, if we are talking about for lead, then we'd be doing T final minus T lead, right? Initial. So then that gives you the change in temperature of lead. Change in temperature of water, H2O, will be then the same equilibrium final temperature, because the two reaches equilibrium. That means the two have the same final temperatures. Okay. All right. So then applying this equation, you'll get actually QPB, right? QPB will be the mass, right, of Pb times C of Pb times delta T of Pb. So let's do this, delta T of Pb plus this guy. So this is that. For the heat of water, we'll be doing mass of water, C of water, and then delta T of water, right? So that goes to 0. Okay. And change in temperature of lead is this guy. Change in temperature of water is actually this guy, right? So we're going to do substitution of this one into there and then this guy into there. So it becomes then MPB, CPB, right? Times, now we'll do TF minus TPB plus MH2O, CH2O, delta T H2O. or actually we'll do, instead we'll do TF minus TH2O, okay? That goes to 0, all right? So now we can see we will have this, all right? And we actually have just everything else. We have the mass of PB, temperature of PB, C of PB, mass of water, T of water, and then C of water. And in this equation, the only unknown would be the TF. Okay, so TF is the unknown, the only unknown in the equation, but there are two TFs. So you will put them together and then solve for TF. Okay, so we should be able to solve for this TF. All right. So what you do is you distribute this guy into the parentheses, right? And then also this MH2O, CH2O into the parentheses, okay? So you'll get MPB, CPB, TF, right? Minus MPB, CPB, TPB plus MH2O, CH2O, TF minus MH2O, CH2O, and TH2O equals 0, right? You'll actually put these two terms, they have TF together, right? And then you'll move these two to the other side of the equation, okay? So these two together, that means this guy plus that guy, right? TF is the common factor, so then you do MPB, CPB, right? Plus MH2O, CH2O, right? Together times TF equals, these two terms go to the other side of the equation. So you get MPB, CPB, TPB plus MH2O, CH2O times TH2O, okay? Then solving for TF, you divide both sides by this, right? Divide this, both sides by that factor. All right. So that means this guy goes to here, in the bottom here, MPB, CPB plus MH2O, CH2O, right? So then at this point, you just plug in all the numbers you have on at the top, right? So all those numbers go into here, and then you have your TF, okay? So let's do that. TF then equals, MPB will be 225 grams, okay? Now CPB, that is 128 joules over kg times K, right? Times TB, 81.2 degrees Celsius, okay? Plus the 155 grams times this guy C H2O 4186 joules over kg times Kelvin, and then times T H2O initially 20.3 degrees Celsius, okay? All this together. So you might want to put a bigger pair of parentheses there, divided by whatever you have at the bottom, add up. So 225 grams times 128 joules over kg times K plus 155 grams, 4186 joules over kg times K. Okay, again, these two add up. So you might want to put a pair of parentheses to just include them together. All right, so you punch all the numbers in your calculator and you'll get your final number as about 22.9 degrees Celsius, okay? Now, you might be wondering, when we have these numbers in here, so the temperatures, right? We actually didn't convert into kelvins, okay? Now, the reason we could do that is because we are actually starting with the equation that has this guy, delta T PB, and then also here, delta T H2O, right? So we are having the differences of those temperatures, okay? So if you convert these two temperature, initial temperature in Kelvin, which you can do that, that's fine. Then you can solve for your TF. Your TF then will be also in Kelvin. Now at the end, you'll just go back and then convert from Kelvin to degrees, right? Or if you just keep the temperatures in Celsius, so then that means this guy will be also in Celsius, right? Celsius minus Celsius, the difference of the two in Celsius actually is the same of the difference of the two in Kelvin, okay? So if we are dealing with delta T, the change in temperature, then Celsius and Kelvins, you don't have to convert Celsius to Kelvins first, okay? So if you stay with Celsius, then at the end, you'll get Celsius, okay? So that's why we didn't have to do that, all right? Now, if you convert into Kelvins here, then that means this guy will be in Kelvin. So at the end, you'll get Kelvin instead of Celsius, okay? It will be then a different number. But then when you convert back to Celsius, then it will be about 22.9, okay? Just keep that in mind. If we are doing delta T, then you don't have to convert Celsius to Kelvin, okay? Normally, you would convert everything into SI unit, but in this case, because we are dealing with delta T, the temperatures are given Celsius, so you don't have to, all right? Okay. So let's go back to the PowerPoint slide. All right. So normally, if this is not specified, we will say specific heat is not it doesn't depend on temperature. But however, you actually in general, if you are covering a wide range of temperature, you'll find actually it depends on temperature. Okay, especially when you go to again the very low temperature, or if you are going to cover a wider range of temperature in that sense. Okay. Now, normally we'll just say specific heat is equal to change of Q 1 over M times change of Q, change of T. So this is coming from delta Q, or Q equals to MC delta T. So you move these two terms to the other side. So MC delta T equal to Q. Q is really change of energy in that sense, okay? So if we are talking about temperature dependent specific heat, then you'll be looking at very small increment of temperature, right? So you take a limit of delta T equal to 0. So then you are doing derivative in this case. So the change sign becomes derivative, okay? So then C equal to 1 over M derivative of Q over dt. So experimentally, this is how you can find the specific heat of a certain material, right? Yeah, changing adding Q gradually and then monitoring the temperature change, okay, in that sense. Then you can calculate that. So let's take a look the example of the temperature dependent specific heat then. So this one says at very low temperature, the specific heat of metal is given as C specific heat C equal to, so this C is the specific heat equal to A, which is a constant number, times the temperature plus B times the temperature to the third power. So for copper, A is equal to 0.0108 joules over kilogram times Kelvin square, and B is equal to 7.62 times 10 to the minus 4 joules kilogram Kelvin to the fourth. It says then how much heat is actually required to heat 1 kilogram of copper from 1.00 to 3.00 Kelvin. So that's very low temperature, okay? So if you have a problem that has the heat capacity is temperature dependent, then you are going to go to the differential form, right? So the one here. So C equals to 1 over m dq over dt. Okay, so you're going to take the equation down, and then you're going to work on this problem here. So let's switch to the camera so you can see the work on the paper here. All right. So we'll do, in this case, you will do C equal to 1 over m, right? And then dq over dt. So you are looking for, so the t goes from 1.00 Kelvin to 3.00 Kelvin, right? So that means this is the initial TI, this is the final TI. This, so you're looking for Q, how much Q, right? It says the mass is 1.0 kilogram, all right? And then C is given as the AT plus B T to the Q, where A and B are given, okay? So I can take down the numbers of A and B, A being 0.0108 joules over kilogram Kelvin square, B being 7.62 times 10 to the minus 4 joules over kilogram times K to the fourth power. All right. So how do we calculate for Q then? So looking at this differential equation, right? So then you probably will rearrange the term. You're going to do, starting from there, you're going to say, okay, so I'm going to multiply both sides by mass and then dt. So mass C and dt then equal, if you multiply both this side by m and dt, that cancels, right? So then you have dq on the other end. All right, now you might feel more comfortable this time because you're looking for q. Then what you do is you do actually integration, right? Integration from the t initial to t final, right? That gives you the change in q. So in integration of dq, that will be given the q, delta q or q. Okay, so let's just say q because we're looking for that. Or you can say delta q, either way, doesn't really matter. Okay. All right. So then you are doing integration here. So integration Ti is 1 Kelvin, right? 1.00 Kelvin. T final is 3 Kelvin. The mass is 1 kilogram. Okay. So let me just take a look on the numbers again. All right, yes, mass is given in 1 kilogram. All right. So it's 1 kilogram, 1.00 kilogram times C as this guy 0.0108 A times T, right? Joules over kg times K square. If you think of the units are messing up with the variables, this is a variable, this is unit, right? So you'll take a look at the unit first. Maybe you may be seeing some cancellations. Okay, so plus, let's do this one first. Put down the numbers first. Joules over kg times k to the fourth, and then t to the third, right? And then dt. Okay. All right. So this kilogram and this kilogram and this kilogram will actually cancel because you distribute this kilogram, 1 kilogram into the two terms, right? So one is just one, right? All right. So then this guy, this is a variable, right? Now these are just the units. So you can just leave them alone. Okay. So this is the dt. So this gives you q or delta q. So t variable dt, right? You're going to square it, right? And you're going to put the 1/2 to that, right? Because once the power you integrate, the power increases, then it brings down 1/2 in front of it. And there's this guy here, still 0.0108, okay, joules over now just Kelvin square times that, plus the second one, right? Now t to the third, you can write down the constant number first, if you want, times t to the fourth power, right? If you raise the power to the fourth, then you bring 1/4 in front of it, right? So this guy, okay? So that's the integration. Now you have the two limits, 1.00k and 3.00k, okay? Equals to delta Q. All right. So then what you do is you plug in the upper limits, right? And then calculate what you get and subtract whatever you get when you plug in the lower limits, right? So you can do 0.0108 over 2. This is joules over Kelvin square, right? Times T square. So it's going to be 3.00k and square, right? And minus, you can do this first, right? This guy, you can do just one term at a time. So it's the first one, upper limit in minus the lower limit, right? And then plus the second term, 7.62 times 10 to the minus 4 joules over 4, right? 1/4, so 4. And then Kelvin to the fourth. Then 3.00 Kelvin, fourth power minus 1.00 Kelvin, Kelvin also fourth power, okay? All right. So you'll see that Kelvin square, right, minus Kelvin square, right, will cancel out this Kelvin square. So the units that will cancel. And Kelvin to the fourth here, this will be Kelvin to the fourth, right? This will be also Kelvin to the fourth. So Kelvin to the fourth will cancel, okay? Now at this time, don't cross the fourth power here, okay? Because you're just getting rid of Kelvin to the fourth. You're not getting rid of the 3 to the fourth or 1 to the fourth, okay? That equals to your delta Q or your Q. So at this point, you can pretty much now plug in the numbers into your calculator, 0.0108 over 2 times parentheses 3 square minus 1 square, right? And then plus 7.62 times 10 to the minus 4 over 4 times 3 to the fourth minus 1 to the fourth, okay? And the result would be 0.0584 joules, okay? We cancel out everything else, but we have joules remain, okay? So the heat added to the metal during this process then will be actually about 0.0584 joules, a small number, because the change of temperature is not a big number, right? It's just about 2 kelvins or 2 degrees Celsius, okay? All right, I think we are going to just stop here for today, okay? So I will see you in the next lecture. Yeah, bye guys.